Hi, I'm Sebastian Medina, and with Cristhian Gomez and Miguel Ortiz, we'd like to present our quantum computing programming project, which is a quiz-kit implementation of quantum reinforcement learning. As a brief introduction, reinforcement learning is a very important area in artificial intelligence that focuses on building intelligent agents that can learn to maximize their reward through trial and error from the environment. This area of learning is a very important area in robotics, finance, natural language processing, and lately, especially in self driving cars. Reinforcement learning has some issues that mainly involve the difficulty of the learning task and the training speed, since learnable parameters in complex RL problems can grow exponentially. That's why a quantum approach can be useful. The work that we'd like to present is based on the paper Quantum Reinforcement Learning by Daoyi Dong, Chunlin Chen, and others, that proposes a quantum reinforcement learning algorithm that may have several advantages over classical reinforcement learning. This is not the first time that we see a quantum advantage in problem solving. Algorithms like Shor's and Grover's have shown how a quantum approach to problems like factoring and search, that are otherwise unfeasible or complex with classical computing, can be solved in an easier way with quantum computation. This algorithm is based on quantum superposition and parallelism, and has the same components as a classical RL algorithm, such as a policy, an environment, and a reward function, and represents actions and states as eigenactions or eigenstates in a quantum system. And by using these natural qualities of quantum theory, we can obtain a much faster and better result than using traditional reinforcement learning algorithms like Q-learning. Now let's go over to Cristhian. He's going to explain the intuition behind the QRL algorithm.
The idea of the QRL algorithm is to use the well-known Grover's algorithm. The algorithm starts with the initialization of all the possible states and all the possible actions that the user can take on each state, which are represented as quantum states. Additionally, we define a value state function, which will determine what is the average reward that the user can gain on each state. Now, for each episode, we will take all the states and make a measurement of the actions, which means that we will observe the action that we are going to take. Now, with that action, we are going to observe the next state and the reward that we achieved. With those values, we are going to update the value state function, and additionally, we are going to use the Grover's algorithm to update the amplitude of the probabilities of the actions of the state, which means that we are going to increase the probability if the reward was as expected or decrease it if it wasn't. The QRL algorithm was tested with the classical problem of path searching inside a maze, in which it was compared the quantum algorithm against the classical Q-table based on neural networks algorithm. The actions of the problem were encoded using 2 bits, as we only have 4 actions: go up, go down, go left, or go right. And the Grover algorithm was implemented for those 4 different actions. Here we have the implementation for the action left, which was encoded as 0, 0, which only increase or decrease the probability of that action. Additionally, we have the implementation for the action up, for the action right, and for the action down. Now, Miguel is going to show you the results of the experimentation and the conclusions.
The reward function graphs from the quantum reinforcement learning and the classical reinforcement learning, we can see that there is a clear advantage of using the quantum reinforcement learning algorithms. The quantum reinforcement learning reach a maximal reward function much sooner in terms of episodes than the classical counterpart. Not only there are benefits in the number of episodes required for achieving a maximal reward function, there is also an efficiency advantage. Whilst the classical reinforcement learning required around 21 minutes to train, the quantum reinforcement learning required only about 1 minute. Given the results of the experimentation, we can conclude that quantum computation can provide powerful tools to improve the current algorithms and novel approaches to solving difficult computational tasks. Implementation and results obtained in this work reflect the natural benefit of involving quantum theory in computational problems, especially related to artificial intelligence. The results show the feasibility of using quantum computation in a practical way and its superiority when problems lie in highly dimensional spaces that may be suboptimal to solve in a classical computational approach.